All right. So, good evening, everyone. My name is Avik Mukhopadhyay, and I am one of the TAs for this course on digital signal processing. And today, in this live session, we are going to cover some sample problems from the contents of week number 11. So, if you recall, in week number 11, we were introduced to the notion of sampling. Then we saw the effects of aliasing, and one remedy to tackle aliasing is of course to use an anti-aliasing filter. And then we saw whether oversampling is really beneficial, as in if oversampling leads to a closer or better approximation or representation of the original signal, whether that's true or not. And finally we concluded with the reconstruction of our signal. So keeping these concepts in mind, let us get started with today's sample problem solving session. Okay, so these are simple true or false questions, question number 1 to 4. So let's solve them one by one. Just quickly let me check the recording. Yeah, all right. So the first question, it says that an anti-aliasing filter ensures that the bandwidth of signal to be sampled is limited to prevent high frequency signals masquerading the low frequency components, masquerading as low frequency components. So this statement is given, and now we need to decide whether it's true or false, and of course with a reasonable justification. So all right, so what do you think? Yeah, so is the question clear? We are looking at question number 1. So any guess whether it's true or false, and if true then why, and if false then why? Any idea? You can make any guess, it's fine. It's, no need to be correct only. We will solve it anyways. We'll see it. So these are basically conceptual questions. These are true or false questions. So just based on the concept, yeah. So Ajit, any idea? So no response. Let me then. So we are studying digital signal processing, and this is week number 11. Okay, and we are looking at the true or false section and discussing question number 1 at the moment. So once again, if you go here in question number 1, so it says that an anti-aliasing filter ensures that the bandwidth of the signal that is to be sampled is limited in order to prevent high frequency signals masquerading as low frequency components. So if you just revisit your lecture videos or your notes, lecture notes, then it should not take you long to conclude that it is indeed true, because that's what we saw during the discussion of anti-aliasing filter. So what happens in aliasing is that if you undersample your signal, if you don't sample, that is by undersampling I mean if you don't sample the signal at the minimum required rate, that is, if you sample below the sampling rate, Nyquist rate, which is twice the maximum frequency component of the signal, if you sample below that threshold or that critical frequency, then aliasing will occur, that is, overlaps will occur, leading to the distortion of the signal. And what happens as a result of that overlap is that we have seen through diagrams that the high frequency components which are present in the signal are masquerading as low frequency components actually. So we'll see that, we'll again see that through the diagrams. So that is what aliasing is, and of course the remedy to deal with aliasing is to use an anti-aliasing filter, and the purpose of the anti-aliasing filter is to basically band limit the input signal. Okay, so this is actually true. So alright, okay, so this is actually true, and so let the justification is as follows. So I'll write justification. So let's assume that we have an infinite duration sinusoid signal. So in its Fourier transform spectrum, we will have basically one frequency, of course, like omega naught, and its reflection minus omega naught. So we'll have such a spectrum. So let's say okay, so let there be an infinite duration sinusoid signal thus its Fourier transform will have two frequencies basically. It's like omega naught and minus omega naught in the spectrum. Okay, so let the frequency of the sinusoid be, let's say f naught equals some 8 kilohertz, and this is exactly the example that was discussed in the lecture. So it will be a recap of the lectures as well, hopefully. So if we have this 8 kilohertz sinusoid, then in the spectrum, in the Fourier transform, you expect something like this. So if the x-axis is frequency in kilohertz, let's say this is so one component will be here, you'll have one impulse here, so this is at f equals to 8 kilohertz, and of course its reflection about the y-axis, which is at f equals to minus 8 kilohertz. Okay, and this center is of course the f equals to 0. So this is how the spectrum will look like. Alright, so now we remember in sampling what we do is we first multiply the given continuous time signal. In this case we have a sinusoid, right? We have an infinite duration, let's say cos omega naught t or sin omega naught t, whatever you can take. We multiply that given time domain sequence signal, continuous time domain signal, by the impulse train, right? That summation k running from minus infinity to infinity delta of t minus kt, right? So you multiply with that impulse train and then take the Fourier transform basically. So multiplication in the time domain translates to convolution in the frequency domain. So it was derived in the lectures that if you do that, then the sampled the Fourier transform of the sampled signal with impulse train that you get is actually the repetition, periodic repetition of this Fourier transform of the continuous time signal, which is shown here in this diagram. So we'll have repetition, periodic repetition of this spectrum, and the period will be the sampling frequency, basically omega s. And another thing is that it will undergo an amplitude scaling by a factor of 1 by capital T, where capital T is the sampling interval, which is the basically reciprocal of the sampling frequency, right? So two things: one is amplitude scaling by factor of 1 by capital T, and periodic repetition, with the period being the sampling frequency omega s. So okay, and so this is we are actually looking at an example of aliasing, right? Just to give you an idea, this is an example of aliasing. And of course you remember that aliasing occurs whenever there is undersampling. You are sampling at an inadequate sampling rate frequency. So in this case, so here your maximum frequency is what? It's 8 kilohertz, right? So minimum sampling rate must be twice the maximum frequency, which is 16 kilohertz. And this is why this is minimum, provided to avoid aliasing. So we need to sample at twice the maximum frequency in order to avoid aliasing, avoid overlap. So now, since aliasing is occurring here in this example, so of course the sampling frequency must be less than this minimum value, must be less than 16 kilohertz. So let's say the sampling frequency f is 10 kilohertz. So this is inadequate, right? because it is less than the minimum required to avoid aliasing. So okay, so now let's say this is 10 kilohertz is the sampling rate. So this spectrum here shown in the diagram will undergo again two things. One is amplitude scaling by a factor of 1 by capital T and periodic repetition. So and with the period equal to Fs, the sampling frequency, so which is chosen as 10 kilohertz here. Okay, so the spectrum of the impulse train sampled signal will be as follows. So you exactly take this x of f shown here and do the two things. Okay, so this will be xs of f. It's the spectrum of the impulse train sampled signal. Okay, this is 0 centered. Okay, initially we had these two, right? At 8 kilohertz. Okay, so this frequency is in kilohertz. Okay, so at 8 kilohertz you had one component, and of course at minus 8 kilohertz you had one component. This was xc of this was x of f, right? And now, and this amplitude, if initially this amplitude was, let's say, 1, this will get, so I'm writing it here also, let's say initially this height was 1, let's say, then here this height will be 1 by capital T. So this is the amplitude scaling which occurs. And what is T? T is simply 1 by Fs. This is the reciprocal of the sampling frequency. Okay, so this is one thing. And second thing which it undergoes is the periodic repetition. And periodic repetition after every Fs duration. So the period is Fs. So Fs we have chosen as 10 kilohertz. So 10 kilohertz will be, so what happens at the origin at f equals to 0 will now shift to f equals to 10, which is the period. So let's say this is at, not this, if this is 10, then okay, we have a component at f equals to minus 8 kilohertz. Now that will get shifted by minus 8 plus 10. Okay, so which is 2. Let me use a different color. So you will have one component here. So this is 2. And similarly this component at f equals to 8 will shift to 8 plus 10, which is 18. So let's say something like this here. Okay, and same will apply on the negative side as well. So if you have on the negative side, if you go 10 units, so let's say this is minus 10, right? Not that far. Of course this is not drawn to the scale, so let's say somewhere here. If this is minus 10, then this frequency at minus 8 will get shifted to minus 8 minus 10, which is minus 18. So it will be somewhere here, let's say minus 18, and this component at f equals to 8 will shift to 8 minus 10, which is minus 2. So minus 2 will be somewhere like here. Alright, okay. Great. And remember that now we are actually interested within the spectrum of minus fs by 2 to fs by 2. Okay, so we are interested within minus fs by 2 to fs by 2. That is, here fs is 10 kilohertz, right? So minus 5 kilohertz to 5 kilohertz. So that will be basically this region, right? This region, this is minus 5, this is plus 5. Okay, so within minus 5 to plus 5, if you see, you have two components, f equals to minus 2 kilohertz and f equals to 2 kilohertz. You don't really have your original spectrum within this interval. Initially you had just minus 8 kilohertz and 8 kilohertz. Those frequency which were higher, 8 kilohertz, that is now hiding, as if it is hiding or masquerading as a low frequency component which is equal to 2 kilohertz here. See, this is how the high frequency components are masquerading as low frequency components. This is the problem of aliasing basically. So this is the thing. So let's go to the next page. This is the thing. So the remark is that therefore a 2 kilohertz, now we have 2 kilohertz component now appears in the spectrum. Between minus fs by 2 to fs by 2 and this is actually the result of the original 8 kilohertz signal being sampled at an inadequate sampling frequency of 10 kilohertz. All this problem has occurred because we undersampled it. The minimum required to stop overlapping or to avoid aliasing was to use 16 kilohertz, but we had used 10 kilohertz, right? That was inadequate. So hence a high frequency signal, namely 8 kilohertz, that was the starting frequency of our original signal, right? A high frequency signal, namely 10 kilohertz, masquerading as a lower frequency signal, which is here 2 kilohertz. Is masquerading because of undersampling. Okay, this is the idea. And now we know that whenever we have time limited signal, so if it is limited in the time domain, that implies it is unlimited in the frequency domain, so it is band unlimited or infinite bandwidth. So, and vice versa, when we have it's like time unlimited, band limited. Okay, that's a rule. And all practical signals are time limited, and therefore they are band unlimited. So it's an infinite duration in the Fourier representation. So we won't be able to sample them without causing aliasing. Okay, and this anti-aliasing filter what this does is this band limits the input signal. So this band unlimited condition is now mitigated. Now this will help us to prevent or avoid aliasing. See, so that is the idea. Okay, so this is of course the statement that was given is actually true. And by the way, in this spectrum, the periodic repetition, here I have shown only for one repetition on both sides, on the positive and negative sides. It will repeat after every 10 kilohertz. So there will be another repetition at 20 kilohertz, right? And you see that this, of course I missed this 2 kilohertz you have right here. You have a component here. So this 2 kilohertz will again repeat after 2 plus 10, which is 12. Okay, similarly minus 12 will also be repeated after, on the negative side, at minus 12. Okay, so this is how the repetition occurs. Okay, right. So that's the entire story that's going behind this question actually. Anyways, so we took a lot of time. Now in the second question, it's again based on what we have learned, that if omega naught is a frequency within 0 to pi interval, if it's a frequency of a real valued sinusoid component in the DTFT spectrum, given this information, can we deduce the underlying true frequency capital omega naught in radian per second of the corresponding continuous time sinusoid? So whether this is true or not. Okay, this statement is claiming that, okay, if I have the knowledge of the frequency omega naught in the DTFT spectrum, based on this information alone I can deduce the true frequency capital omega naught of the original continuous time sinusoid signal. So we need to claim whether this is true or not and why. So, and if you again recall your lectures, you should be able to answer that this is what, true or false? This is false, right? Okay, why this is false? So let us try to understand the justification. Okay, so let's say we have one continuous time signal x of t equals to cos 2 pi f naught t. Okay, let f naught with f naught equals 8 kilohertz. Okay, this is an 8 kilohertz sinusoid continuous time signal. So if 8 kilohertz is the frequency of this signal, then the sampling frequency that is enough is 2 times 8, which is 16 kilohertz, to avoid aliasing, correct? So 16 kilohertz is enough, but let fs equals to the sampling frequency equals 24 kilohertz. So 24 is surely greater than 16, so we have more than enough. Okay, and now the sequence, discrete time sequence is, remember when we had the continuous time signal, we are basically sampling at after every capital T instance, right, to get the sequence x of n. So x of n is x of capital N T, right, and capital T is basically the reciprocal of the frequency. So this is this, and if you just replace the t here in this x of t by n by fs, you get like this. Okay, and now 2 pi f naught is what? It is 8, and fs is what? 24. Okay, so this is how much? 2 pi by 3 n. Okay, fine. So this is the sequence. Okay, discrete time sequence. Okay, great. Now let's say if you have another or basically, so if you choose the same continuous time signal, let's say this time I am using the literal y to denote just it's a separate case. So if y of t is again that old thing, but this time why I am choosing y here as a different literal, because this time let's say, so previously in the previous case we had f naught equals to 8 kilohertz, right, and fs equals to 24 kilohertz. Now let's say this time we have f naught equals to 16 kilohertz. Okay, and fs, let's say, now what is the minimum fs that you need to avoid aliasing here? Twice of f naught, which is 32 kilohertz. Let's say I have more than that, let's say I have 48 kilohertz as the sampling frequency fs. Okay, so then your discrete time sequence y of n would be like we saw in the previous case. So it's y of n times capital T, this is n by fs. Okay, this is cos, again cos 2 pi f naught, you replace t by n by fs, so you have this. This is cos 2 pi times 16 n by fs is 48, so this, and this is again exactly 2 pi by 3 n, you see. So clearly, like in both cases we got the same discrete time sequence. So we have the exactly same DTFT, right? Okay, exact same DTFT spectrum in both cases. Okay, the thing is, if you so ultimately what's the frequency that will be present in the spectrum of DTFT? It's 2 pi by 3, right? Cos 2 pi by 3 n is here. So if you take its DTFT, you will get one component would be here at omega naught, which is 2 pi by 3, and of course you have here at minus 2 pi by 3. Okay, and of course this is, let's say, pi, minus pi to pi. You will have this. Okay, or basically both. So if you either take the spectrum of x of e power j omega or y of e power j omega, it's the same. So now, given this spectrum, actually so you see, in both cases we will have the exact same spectrum, and the frequency component that will be visible in this spectrum is 2 pi by 3 and its reflection at minus 2 pi by 3. Now, but we get the exactly same identical spectrum for both the cases. The cases are different, right? So this was case 2, and this was case 1. So we had different f naught and fs in the two cases, right? In the first case we had f naught equals to 8 kilohertz and fs equals to 24 kilohertz. In second case we had f naught equals to 16 kilohertz and fs equals to 48 kilohertz. But we end up getting the exactly identical spectrum in the DTFT. So we won't be actually able to say like from which continuous time signal this spectrum actually came. So what was the original time domain signal, we won't be able to actually decode from this given spectrum. Okay, isn't it? So we won't be able to say whether the original signal was 8 kilohertz signal comma sampled at 24 kilohertz, right? That's the first case. Or a 16 kilohertz, or whether it was a 16 kilohertz signal sampled at 48 kilohertz. So this we can't tell. We can't tell unless we have the information or the knowledge about what? The sampling frequency. if we had known the sampling frequency, then okay, then we have one more information in our hand, and we would be able to actually go back and see from which time domain sequence or signal this spectrum we got. Okay, so in that case we will be able to decide whether it was case 1 or case 2 if we had been given the information about the sampling frequency, right? So in this case what's happening basically, if not by FS ratio is basically same as 2 times F naught by 2 times Fs, right? So if F naught was 8 kilohertz and Fs was 24 kilohertz in the first case, remember in the first case F naught was 8 kilohertz and Fs was 2 kilohertz, 24 kilohertz, right? In the second case F naught was 16 kilohertz and Fs was 48 kilohertz, you see. So the values just got doubled, but this ratio of F naught to Fs, this remains the same, isn't it? So this ratio actually is deciding, since the ratio is the same, the spectrum is exactly the same, you see. That is what is expected. So given this spectrum, given this knowledge of omega naught only, we won't be able to actually go back to our original continuous time signal. Okay, so this is false actually. True? I hope this is clear. So you're done with question number 2. Now let's go to question number 3. Okay, we are given a continuous time signal, xc of t equals to 2 times cos 20 pi t plus 3 times sin 60 pi t minus cos 50 pi t, and the question says that the Nyquist sampling rate for this signal is 60 Hz. This is given. Now we need to decide whether it is true or false. Okay, it's a question based on Nyquist sampling rate calculation, so we'll just quickly go through it. Alright, so question number 3. Question number 3. So we don't know the answer yet, whether it's true or false. Let us solve it. It's a numerical question, so let's solve it and then decide whether it's true or false. Okay, so the given, again this is the justification. So the given signal is 2 times cos 20 pi t plus 3 times sin 60 pi t minus cos 50 pi t. Given that Nyquist rate is 60 Hertz. Okay, so it's not in radians per second, it's in Hertz. So we need to check whether this is true or false. Okay, so what's the way to find the Nyquist rate of this signal? So you see this signal xc of t has 3 different frequencies, right? Okay, so let me just name them. So first frequency is 20 pi t, right? So 20 pi is the first frequency. If you compare with cos omega naught t form, then omega naught is, for the first term we have omega naught equals to 20 pi. Okay, so this is my first frequency, 20 pi. Let me call this omega 1. Similarly, the second frequency is 60 pi. Let me call this omega 2. Similarly, the third one is omega 3, which is 50 pi. Okay, okay, so omega 1 is 20 pi, and remember this is in radians per second. Okay, so but the Nyquist rate is given in hertz, so we need to convert it to hertz. So f1 would be basically omega 1 by 2 pi, which is 10 hertz. Sorry, 10 hertz, not kilohertz. Fine. Similarly, omega 2 is 60 pi radians per second. Fine. So your f2 will be omega 2 by 2 pi again, which is 30 hertz. Finally, we have omega 3 f3 will be 25 hertz. Alright, now the next step is to find the maximum frequency out of these given frequencies. So therefore f max is basically the maximum of this list, and clearly you see the maximum among f1, f2 and f3 is f2, which is nothing but 30 hertz. So we have found the maximum frequency component. Now it's just, we are done. The Nyquist rate will be, what's the Nyquist rate? It's exactly twice the maximum frequency, right? 2 times f max, so which is 2 into 30 equals 60 hertz. So indeed this was given in the question, right? In the in the statement we were given that Nyquist rate is 60 hertz, and we were to decide whether it's true or false. So yeah, we calculated that it is indeed equal to 60 hertz, so this is true, right? So this is true. Fine, this was simple. Now lastly, the fourth question. In the fourth question, we are given that Xc of t is a low pass signal and it is band limited, and it is sampled such that there is no aliasing, and if this Xc of t is oversampled, the corresponding sequence x of n is a closer or better representation of Xc of t. So this is another concept that was already covered in the lecture videos. This is the like a check on whether oversampling leads to better or closer approximation or representation of the time domain signal Xc of t. Okay, so and it was shown that it is not the case. So oversampling is not beneficial in this regard. So if you are sampling above the Nyquist rate, it's fine. You are avoiding aliasing, it's fine. And if you are oversampling it, it won't make any difference, right? Rather, it creates some problems, as we saw. So we saw that if we are sampling at a higher sampling rate, then through diagram we actually visualized that the signal which is sampled at a higher sampling frequency will occupy a narrower bandwidth in the frequency of the DTFT domain. Remember, and so hence the higher sampling rates basically lead to signals with spectrum that are narrow, and if the spectrum is narrow, if they occupy a narrow bandwidth, let's say for higher frequency sampling rate, then let's say if you have a practical scenario when we have noise added to the signal, okay, so we have signal plus noise, and if that signal is of narrow bandwidth, which is the case when you go for higher sampling rate, then in order to remove the noise from that signal, if this bandwidth occupied is narrow, then you will need a filter which is also narrow. So the conditions on the filter is very stringent. There are a lot of restrictions. You need to come up with a filter that also has a narrow bandwidth, right, in order to remove the noise acting on the signal. Whereas if you sample at a lower frequency, then you don't have this trouble. In that case, the signal will occupy a broader bandwidth in the DTFT domain, and then you don't have such restringent conditions or restrictions on the filter, right? So that is the advantage. And also another fact is that if your sampling frequency is high, if you're sampling at a higher rate, then it means that at the receiver you will receive more samples quickly, right, at a faster rate, right, because you are sampling at a faster rate. In order to see, so you will need more complex architectures and more complex hardware to come up with such DSP processors that are able to actually cope up with that speed. So you need to process your incoming samples at such a higher pace. In that case, if the sampling rate is high, okay, you need processor with higher MIPS, okay, whereas if you sample at lower frequency, then you don't have this trouble. By lower frequency, I don't mean that you are doing undersampling. Lower means the so the proper frequency to choose is an adequately sufficient frequency, okay, which is above the Nyquist rate, okay, not below that, otherwise you will have undersampling and aliasing. Just choose an adequate frequency in the discrete time case, that's it. You don't need to oversample it, don't need to pick a large sampling rate, because it will lead to these problems. So we have discussed all these things. So this statement is actually, it is saying that oversampling is actually helping to come up with a closer or better representation of the time domain sequence signal X of t, which is not true. It's not true. We have looked at it in the lectures. So this is false. This is false. Justification. Just refer to lecture notes or videos. Okay. just few points in this regard. First was that oversampling does not lead to a closer or better representation of the original signal. So you might think, like, if we have a original signal like this, let's say xc of t like this, you might think that, okay, if I sample more frequently at a higher frequency, if I take more and more samples more frequently, right, like this, then I might actually be reconstructing my original signal I am more closer to an exact recovery or closer approximation of the original signal, but that's not the case. Okay. Like I said, this was already discussed, that higher sampling rates lead to signals with spectrum that are narrower. Okay, and for higher sampling rates, we need a processor with higher processing speed, right? So this is another burden. Okay, just recall your lecture notes, you should be fine. Alright, so we are done with the true or false section. Okay, and we have looked at all the true or false questions in a very elaborate manner, step by step, so that the underlying concept is clear to all of you. Okay, all right, now let's move on to question number 5. Okay, so in question number 5, we are given a signal x of t, and it is mentioned that x of t has a Nyquist rate omega naught. Given this information, we need to now determine the Nyquist rate for each of the following sequence. So in A, B, C, D, we have some functions of x of t, or some other forms actually, and we need to find the Nyquist rate for those signals. Okay, and I think you have a similar problem in the assignment 11 also, like this question number 5. So it might be useful for those who have not yet solved that problem. Anyways, okay. So let's see question number 5. Okay, x of t, right? Just let me just go to the x of t. Okay. Because sometimes you have xc of t in the continuous time signal notation, and sometimes you have x of t. That's why I just needed to check it. So x of t has Nyquist rate omega naught. This is given. Now so Nyquist rate, we know that it is twice omega max, the maximum frequency. Yeah, so omega naught is the Nyquist rate and it is twice omega max. So omega max would be omega naught by 2. So we can say that the maximum frequency component in the Fourier transform of x of t, that is in x of j omega, is this omega max, which is omega naught by 2. Okay, that's the maximum frequency, and beyond that frequency, the Fourier transform is 0, isn't it? So just a second. Maximum frequency component in the Fourier transform of x of t, that is in x of j omega, is equal to omega naught by 2. That's the maximum we just calculated, maximum frequency component. And beyond this frequency, our Fourier transform will be 0, right? So x of j omega is 0. This implies it's 0 for mod omega greater than omega naught by 2. Okay, so you can imagine pictorially something like this. Okay, this is minus omega naught by 2, this is omega naught by 2. This is the maximum, this is omega max. Beyond this point, both in the negative side and positive side, the spectrum is 0 basically, it vanishes. Alright, so now if you go to the question, in part A, we are looking at part A, the signal is now x of t plus x of t minus 1. So we have the original signal plus a delayed version of the signal by one sample. So okay, fine. So now let's see part A. So we have y of t. Let me call this y of t because it's a different signal now. X of t plus x of t minus 1. So if you take Fourier transform on both sides, what do you get? Y of j omega. And here again, like I'm using this notation, y of j omega for the Fourier transform. So there might be a slight abuse of the notations from what we have seen in our previous lectures. So, but just for now, you make sure that this is just the Fourier transform of this continuous time signal. Okay, right. So this is plus. Now what happens to the Fourier transform of x of t minus 1? It will, so we need to use the time delay property of Fourier transform, right? So if you have, let's say, x of t minus t naught, its Fourier transform would be, will have an exponential multiplication, right? E to the power minus j omega t naught, the delay unit, and x of j, correct? So if you use this delay property here, then what do we get? E power minus j omega t naught is basically 1, and x of j omega. And here we are taking Fourier transform on both sides. All right. So I can club this together, like I can take what I mean to say is I can take x of j omega as common, and this is the factor. So when is my y of j omega 0? Y of j omega 0 equals to 0 implies x of j omega plus this is 0, right? Now this factor 1 plus e power minus j omega, this certainly goes to 0 if omega is like plus minus pi, that's fine, but that's only just one case, one value of omega for which it goes to 0. But otherwise, if you have to guarantee this entire expression to go to 0, to be 0, then the first part, which is x of j omega, that should be 0, right? That is 0, then you are guaranteed that it will be always 0 overall. Okay, so what I will write is therefore, so y of j omega is guaranteed to be 0 when this x of j omega is a factor, right? When x of j omega equals to 0, that is, now when is x of j omega equal to 0? We just saw that x of j omega equals to 0 for mod omega greater than omega naught by 2. So this happens when mod omega is greater than omega naught by 2. Alright. So again, this omega naught by 2 is again the maximum frequency for y of j omega. So its Nyquist rate would be twice of that. It's again omega naught. So it will be the same basically. Hence the Nyquist rate for y of t is also omega naught. Alright. Okay. I hope this is clear. So it doesn't change actually. If you add another delayed version of the signal, we see that this doesn't actually change, because still the condition on y of j omega to go to 0 is that is guaranteed only if x of j omega goes to 0. So this spectrum of like the limits on spectrum of y of j omega will also from minus omega by 2 to omega by 2. Outside that it is 0 again, it goes to 0. So omega max for y of j omega is also omega naught by 2. So the Nyquist rate is twice of that, which is omega naught. Okay. So this is how you solve these kind of problems. And now let's go to part B. Part B is the derivative of this signal, d dt of xt. So dx dt. So you have y of t equals alright. Sorry for the bad handwriting. Now what happens to y of, again we will just follow the same procedure. So we'll take the Fourier transform and then check when is that Fourier transform guaranteed to be 0, and depending on that omega max limit we can come up with the Nyquist rate for this signal. So again let's take the Fourier transform. If you take the Fourier transform, you have y of j omega equals, if you have a derivative in the time domain, what do you have in the frequency domain? This will translate to j omega times x of j omega, right? Isn't it? Even in the continuous time case, when we used to solve the differential equations, right? If we had a term of the form dx of t dt, then on taking the Laplace we used to get s times x, capital X of s, right? So exactly the same thing is happening here, just s is j omega, so j omega times capital X of j omega. So this will be the Fourier transform, and again you see it's y of j omega is same as x of j omega multiplied by a scaling factor of j omega, that's it. So again, clearly y of j omega is guaranteed to be 0 when x of j omega is 0. That is for mod omega. Again same, this condition is known to us when x of j omega is guaranteed to be 0, that is mod omega greater than omega naught by 2. Again, so hence Nyquist rate will be the same. Okay, now moving to the part C, we have squared signal, so x square of t. Okay, so this is part C. So y of t is this. Okay, now I can write it as x of t times x of t, multiplication in the time domain. Now what happens if we have multiplication in the time domain? We know multiplication in the time domain translates to convolution in the frequency domain. So if we take Fourier transform, you will get, of course, a factor of 1 by 2 pi will be there, and this will be convolution. Multiplication will be replaced by convolution. Right? Fine. Now you see, this is like convolution with self. Okay, the spectrum is convolved with itself basically. So like the duration, what do you expect in the overall duration of this convolution? If the bandwidth is like omega naught for the individual spectrum x of j omega, then on convolving it with itself, the overall bandwidth would be twice, right? So it will be 2 omega naught. So what I mean to say is, so remember you had the diagram for x of j omega like this, right? So for the sake of simplicity, we chose a rectangular pulse. So between minus omega naught by 2 to omega naught by 2. So this was, I'm drawing it again. Alright, you had this. Now if you want to check the spectrum for this, what do you expect? So you are convolving again. Like, anyways, so if you convert this rectangular pulse with itself, what do you expect? The resulting spectrum will be a triangular waveform, right? And its duration would be double. So because convolution is nothing but taking the copy of the signal, so hence here we are convolving this signal with itself, so we are taking its copy and then shifting it and sliding it across its window, right? So from left to right, you can imagine. So this is should be something like this. This point would be minus omega naught, this point would be omega naught. Okay, this is the thing. So now y of j, which is basically 1 by 2 pi of this thing, y of j will be now guaranteed. So y of j takes up the spectrum, it's non-zero from minus omega naught to omega naught. Outside this window it is 0. So y of j omega is guaranteed to be 0 for mod omega greater than omega naught. Okay, so basically the y max, sorry, w max, the omega max, maximum frequency for y of j omega would be omega naught, right? And we observe that Nyquist rate will now be twice of this omega max, which is 2 times omega naught. So this is, see, Nyquist rate got doubled because here y of j omega occupies double bandwidth, right? So beyond this omega naught or minus omega naught, the spectrum will be 0. Okay, so the Nyquist rate is twice of that maximum frequency, which is 2 omega naught. Alright, so good. So in this example we saw that the Nyquist rate is different. So similarly, let's see the last part D. So we have x of t multiplied by cos omega naught t. Okay, let me go to the next page. So y of t here is x of t times cos omega naught t. Again we will follow the same process. So if you take the Fourier transform, so you get y of j omega would be, so what will be the Fourier transform of x of t times cos of omega naught t? This will be So there will be two frequency shifts, right? Omega plus omega naught and omega minus omega naught. So, and of course the factor of half would be there. So this will be first component plus half x of the second component x. In case you are wondering, this should be familiar, but still if you want a quick proof, so the Fourier transform of, we are looking at this, right, on the RHS. So this is integration e power minus j omega t dt, correct? And now this cos omega naught t is e power j omega naught t plus e power minus j omega naught t whole divided by 2, right? This is a known formula. So if I take that half factor outside, I can write this as e power j omega naught t, first term, plus e power j minus j omega naught t, the second term, correct? So this is I can write the first term as like this, taking minus j common, right? So now it's done. So the first term is, this will be basically is the Fourier transform of x of t, but the frequency is shifted by omega naught. Okay, so this is this x of capital X of j omega minus omega naught, right? And the second term is, you can already guess, omega plus omega. See, exactly this what we have written here in the blue ink, right? Anyway, so continuing, so okay, so if you had your capital X of j omega like this, again I am drawing that old diagram. Let's say if it was like this, so now we are looking at this, right? This half x of j omega minus omega naught plus half cap x of j omega plus omega naught, this whole term we are looking, and let's look at it term by term. So let's first look at the first term, which is half x capital X of j omega minus omega naught. Okay, okay, so we want to visualize half capital X of j omega naught omega minus omega naught. This so what would it look like? So you see, first of all we have an amplitude scaling by a factor of half, so this amplitude would become half, and we have a frequency shift omega minus omega naught, so it's a right shift by omega naught units, correct? So this 0, this origin will move to omega naught. Similarly, this omega naught by 2 term, this place will move to omega naught by 2 plus omega naught, which is 3 omega naught by 2, right? And this minus omega naught by 2 will move to minus omega naught by 2 plus omega naught, which is omega naught by 2. So it will look like this. Right. This point is 3 omega naught by 2. This point is omega naught by 2, and the amplitude is half. Hopefully you can understand. Amplitude gets reduced by a factor of half, and similarly now you do for the second term, which is half x capital X of j omega plus omega naught. So it will be on the left side. Basically it's the same thing on the left side. Right, it will be the same thing on the left side. So we'll have one more copy here. Now if I want to, basically what I am doing is I'm also including this second term, and remember this is our altogether, this is capital Y of j. So this term here, the second term here, will have exactly this kind of spectrum, but it will be on the left side. So you can expect something like okay. So and the point would be, so this will be minus omega naught by 2, and this would be minus 3 omega naught by 2. Fine. Great. So see, we have drawn the spectrum for y of j omega. Now so this y of j omega exists up to what point? 3 omega naught by 2 on the positive side, and similarly minus 3 omega naught by 2 on the negative side. So this will be, this point is now our this is now our omega max, right? So beyond this 3 omega naught by 2, y of capital Y of j omega is 0, right? It's guaranteed to be 0. So it's guaranteed to be 0 for omega beyond 3 omega naught by 2. Okay, mod omega takes care of basically the negative terms also, because we are looking at both sides, negative and positive sides, right? So that's why we have mod. So that's the thing. So this omega max for capital Y of j omega is equal to 3 omega naught by 2. So the Nyquist rate for y of t would be twice of this omega max, which is 3 omega, right? Nyquist rate for y of t is twice of 3 omega naught by 2, which is 3 omega naught. So you see, again in this example also the Nyquist rate changes by a factor of 3 basically. X of t had Nyquist rate omega naught, but in this example part D, I think y of t has Nyquist rate 3 times omega naught. Okay, fine. So now coming to the 6th problem. Alright, impulse train sampling of x of n is used to obtain another sequence g of n, which is summation k running from minus infinity to infinity x of n times delta of n minus k times cap n. So basically what we are doing is, we have this sequence x of n and we are doing the impulse train sampling. We are multiplying x of n by this impulse train, which is k running from minus infinity to infinity delta of n minus k times cap n. Cap n is the sampling interval basically, and on multiplying this we are getting another sequence g of n. Fine. Now the DTFT of x of n, which is capital X of e power j omega, if this is 0 for the interval 3 pi by 7 to pi, okay, whenever like 3 pi by 7 less than or equals to mod omega less than or equals to pi, if this spectrum is 0, determine the largest value for the sampling interval capital N, which ensures that no aliasing takes place while sampling small x of n. Okay, alright. So again this is based on the sampling theorem, the condition basically, the Nyquist rate. That's it. It's a very simple problem in hand. Okay, so let me check if again is going on. Alright, so go to the next page. So looking at question number 6. So it is given that after impulse train sampling, after multiplying with the impulse train, you get when x of n is multiplied with the impulse train, you get a new signal g of n like this. Fine. And so where n is the sampling interval. So remember, in our lectures we use the notation capital T. So here basically capital N is playing the role of capital T. It is the sampling interval, or which is the reciprocal of the sampling frequency, right? Okay. And it is given that capital X of e power j omega is 0 for this interval. Okay, so we can imagine something like this. So if you try to visualize the spectrum, okay, spectrum will be something like this. See, within 3 pi by 7 to pi, this is 0, and again on the negative side between minus 3 pi by 7 to minus pi, it is also 0. Only within minus 3 pi by 7 to plus 3 pi by 7 it is existing, it is non-zero. Okay, the spectrum is non-zero. So clearly this particular point, frequency 3 pi by 7, this is our omega max, correct? So omega max just a second. Oops, I think, oh my god. Oh my god. So this document, I think, didn't respond. This is unfortunate. Anyways, this is unfortunate. So I don't know why this happened, but so let's continue. So you can anyways check the solutions from the video itself. So so everything is recorded, but PDF will be not complete. So anyways, okay. So I'll make a note here. For solutions of question 1 to question 5, kindly watch the video recording. Okay. Anyways, it's unfortunate that the document was not saved, didn't respond, some technical issues. So anyways, we were in question number 6. So again, so question number 6, this was the thing, right? So I had written down, correct, this was given, and the DTFT was 0 for this interval, so if you try to visualize the spectrum, it would look something like this. So this spectrum exists only from minus 3 pi by 7 to 3 pi by 7. Only within this window it is non-zero, and from 3 pi by 7 to pi on the positive side it vanishes. Similarly on the negative side, from minus 3 pi by 7 to minus pi, it is again 0. So this is how it would look like. So you see clearly this end point, which is 3 pi by 7, this is our omega max for this spectrum, correct? So omega max is 3 pi by 7, alright? And now for no aliasing, what is the condition? The sampling frequency must be at least twice the maximum frequency component. Okay, so omega s must be at least equal to 2 times 3 pi by 7 so 6 pi by 7. And what is capital omega s? This is 2 pi fs, you can write. Okay, and fs is what? 1 by capital N. So the frequency is the reciprocal of the sampling interval, so this becomes 2 pi by capital N. It's not equal to, it's greater than equal to. So since okay, cancel this becomes 3. So you get n is less than or equal to 7 by 3, and 7 by 3 is nothing but some 2.3333, so on it continues. So what is an ideal value for integral value for n? So the maximum it can go is n equals to 2, right? N has to be an integer, of course. So this is 2. So see, we have found the value of n. The question we were asked to determine the largest value of the sampling interval. So this is 2. Okay, capital N is 2. If we sample at every 2 consecutive samples, then we can actually do the recovery without aliasing, right? So that's it. So we are done with question number 6 now. Now this is the last question. Basically it has two questions sub part. So the main question is like this: we have a continuous time signal c of t with the Fourier transform given by this diagram here. Okay, we have capital Xc of f plotted as a function of capital F. So the frequency here is in kilohertz. Okay, the signal is sampled with sampling rate is capital Fs. Okay, to yield the discrete time sequence which is x of n, and the DTFT of x of n is, as you know, capital X of e power j omega. Now this condition is given, like from 3 pi by the integration from 3 pi by 4 to pi capital X of e power j omega d omega is exactly equal to a times pi. Okay, this is given. A is any variable. Okay, so this integration of the DTFT from this 3 pi by 4 to pi interval is equal to a pi. Now we need to answer these following questions. If the sampling frequency Fs is 10 kilohertz, then what is the value of A as per this constraint? And if the sampling frequency is 8 kilohertz, then what's the value of A? Simple. So let's see this. Okay, so this is question number 7. So in question number 7 the sampling frequency is 10 kilohertz, it is given. Okay, you see, go back to the question. Fs is 10 kilohertz. Fine. So now if Fs is 10 kilohertz, the sampling time interval is 1 by Fs, so which is 1 by 10 kilohertz, which is 10 into 10 to the power 3 in the denominator. So this, so ultimately our 1 by T is 1 by capital T is 10 to the power 4. Why I am writing 1 by capital T? Basically, it's obvious it will be same as Fs. So if you remember why I am doing this is, two things happen. One is amplitude, scaling, and that scaling occurs by a factor of 1 by capital T. That's why I am concerned about 1 by capital T. Secondly, periodic repetition with period omega is the sampling frequency. So originally we have this spectrum like this. So remember, in question it is in terms of F in kilohertz, so capital Xc of F versus F. But in our lecture notes we have actually plotted this, visualized this in terms of omega, capital omega, where omega is in radians per second basically. So I'll stick to that. So instead of capital Xc of F, we will use capital Xc of capital omega as a function of omega. And all we need to do is, if we need to move from capital F to capital omega, we need to basically multiply by 2 pi, right? Multiply all these values around the horizontal axis by 2 pi. Okay, and if capital F is in kilohertz, then this capital omega would be in kiloradians per second. True? And so we'll have something like this. Okay, it's not drawn to the scale, right? So it won't be accurate, of course. Anyways, roughly it will look like this. So this amplitude was 1, remember, this is the center. Okay, now in the F scale we had this points, endpoints of the triangle as 3 and minus 3. So they will get multiplied by 2 pi, as I said, because we are moving from F to capital omega. So 3 if multiplied by 2 pi becomes 6 pi. This is 6 pi, this will be minus 6 pi. And similarly for these impulses on the diagram, the points are their impulses are located at 3.5 and minus 3.5. So on multiplying by 2 pi, this become 7 pi and minus 7. Fine. Okay. Now, how do we get the spectrum of the sampled signal? Remember, so this what we have drawn is capital Xc of omega. It is the CTFT of the continuous time signal, original continuous time signal Xc of t. And for sampling, we multiply this Xc of t with an impulse train, and then take the Fourier transform of that multiplied overall sampled signal to get the spectrum, which we call by Xs of omega, right? And like I have written in red ink on the side, two things happen to this signal, to the sampled signal basically. First is an amplitude scaling by a factor of 1 by capital T, and secondly a periodic repetition with the period being the sampling frequency omega s. That's it. So we'll have periodic repetitions of this capital Xc of omega after every omega s duration. Okay, so let's see how does it look like. So this is the origin. So, and remember, this will have an amplitude scaling. So initially it was 1, the amplitude was 1, peak of this triangle. So now the peak of the triangle becomes 1 by capital T, which is 10 power 4. So I am not drawing it to the scale, but you can imagine something like this. Okay. Alright. Okay. Alright, so yeah, this will be basically, the height will be 10 to the power 4, and these points are same. Now this pattern repeats after every omega s. So omega s is what? If fs is 10 kilohertz, omega s is 2 pi fs, which is 20 pi kiloradians per second. So now what happens at origin at 0 now goes to 20 pi, right? So you can imagine 20 pi to be somewhere here, let's say 20 pi. Okay. The same thing repeated here. Okay, so this point would be what? Shift by 6 pi, sure. So we have 14 pi, right? Similarly on the right side we have 26 pi. Okay, and the adjacent impulses will be at, so this will be at 13 pi, I guess. Okay, similarly here this will be at 27 pi. Fine, great. And it just repeats on the other side as well. So you go to minus 20 pi, so this endpoints will be minus 14 pi and minus 26 pi, and the impulses will be again at, so this one will be at minus 13 pi and the other one would be minus 27. Okay, I know it's a bit crowded, but hopefully you can get the idea. And this continues on both sides. Periodic repetition happens. Okay, so this is how you get the spectrum of the sampled signal. And now if you want to go to the DTFT, capital X of e power j omega, from capital X s of omega, all you need to do is, if you recall your lectures, all you need to do is you need to normalize the omega axis, the horizontal axis, by dividing by fs, capital Fs basically. So if you divide capital omega by capital Fs, right, what you will get is like this. Okay, just a second, keeps a notification every time. Okay, so now our x-axis will be omega basically, because we are going from capital omega to the DTFT. So the independent variable is little omega and not capital omega. And this, so we are dividing this horizontal axis of capital omega, we are dividing this kilorads per second, this horizontal axis, by capital Fs. So basically on going here to here, we are normalizing the frequency axis by dividing by capital Fs, which in the problem is equal to 10 kilohertz. Fine, great. So now everything is straightforward. So if you divide these values on the x-axis by 10 kilohertz, so if you have 20 pi, this triangle sitting at 20 pi, centered at 20 pi, if you divide 20 pi by 10 kilohertz, what do you get? 20 pi, of course the unit is in kilo radians per second. If you divide by 10 kilohertz, if you divide 20 pi kilorads per second by 10 kilohertz. So what I mean to say is, if you divide 20 pi kiloradians per second by 10 kilohertz, you get 2 pi, correct? Okay. So this is your now, so this 20 pi point will basically be translated to 2 pi, you see, and similarly rest of all these points, this 14 pi, 26 pi, whatever, they will be scaled down by a factor of 10 kilohertz, and we can mark our new points like that. So this one, if you consider this triangle, so the, oh my god, so this is like this, so this 20 pi now gets mapped to 2 pi. Similarly, minus 20 pi gets mapped to minus 2 pi. This is as expected, right? Because the DTFT is 2 pi period. So this excess of omega is omega s periodic. Now the DTFT is 2 pi periodic, correct? And the center remains the same, it's fine. Okay, now about the points. Okay, let me draw the impulses also first. Fine. So now what happens to, let's say, the 7 pi, the impulse, the right impulse in the middle. So 7 pi gets mapped to 7 pi by 10. Okay, 7 pi by 10, which is 0.7 pi, of course. So 0.7 pi, this impulse occurs at 0.7 pi. Similarly, 6 pi. 6 pi gets mapped to 6 pi by 10, so which is 0.6 pi, you can take. This is 0.6 pi. Similarly, this will be minus 0.6 pi, and this is minus 0.7 pi. Alright, we just divide by 10, that's it. Okay, and this omega would be, by the way, in radians per second, because previously you had kiloradians per second, you are dividing by kilohertz. Fs equals to kilohertz, is in kilohertz, so overall you will get radians per second, the unit of omega, little omega. Anyway, so the height remains the same, 10 to the power 4. Fine, no amplitude scaling happens this time. And so again you can do for the rest of the term. So minus 13 pi goes to minus 1.3 pi. This is minus 1.4 pi. This is minus 2.6 pi. This is minus 2.7 pi. Alright, fine. So this is our DTFT. This is the DTFT spectrum, which is 2 pi periodic, of course. Now go back to the question, check the condition which is given. Integration from 3 pi by 4 to pi capital X of e power j omega d omega is equals to a pi. We need to find the value of a. So given 3 pi by 4 to pi cap x of j omega, this is a pi. So what can you say? What is 3 pi by 4? 3 pi by 4 is, since here in this spectrum we have used decimal places, that's why let's convert this fraction 3 pi by 4 to decimal. So 3 pi by 4 is basically 0.75 pi, isn't it? Upper limit is pi. This is a pi. Alright. So now check the spectrum of the DTFT x of e power j omega from 0.75 pi to pi. What is its value? It is 0, right? Because here you see this is the last, this is the impulse occurring at 0.75 pi. Well, and we will have pi. Where is pi? Pi is somewhere like here, between 0.7 pi and 1.3 pi. Similarly, minus pi is somewhere here. Fine. Okay. So this impulse is at 0.7 pi. We are interested in the integral from 0.75 pi to pi. In that region, this spectrum is 0, right? So of course, what will be the value of this integral? It is 0. It is clearly 0. This is 0 equals to a pi. Why? Since the DTFT spectrum is 0, in this range, right? From 0.75 pi to pi. Okay, so the conclusion is a is 0. Fine. So this is the value of a for question number 7, if the sampling frequency is 10 kHz. Now you just do the same thing for sampling frequency equals to 8 kHz. Check what happens. You just follow the same process. You can come up with a similar diagram and check what happens to this integral and what happens to the value of a. Okay, so I will write here only. Similarly, solve question number 8. Look at when fs is 8 kHz. Okay, that's it. So that's it. We have covered all the questions, all the 8 questions here. I mean, the eighth one is just as similar as question number 7. You can try it yourself. So let me stop the recording here, and we'll meet again on next Monday 6 p.m. Thank you.